No matter where you go in the world, the moment people hear the name iPhone, they instantly think of premium design blended perfectly with cutting edge technology. Every year in September, Apple Inc. unveils its latest models, and the entire tech world seems to buzz with excitement. This time, the spotlight is on the iPhone 17 Pro Max, with its stunning orange titanium edition. But have you ever wondered how such an expensive and beautifully crafted device is actually made? The journey begins deep beneath the earth, where high-quality titanium is mined from different parts of the world. This metal is incredibly strong yet lightweight, making it ideal for advanced technological use. The raw titanium is first sent to refining facilities, where it is melted under extreme heat and transformed into large, solid blocks. These blocks are then transported to massive factories, where the real transformation begins. The mining operations that supply Apple with its titanium are scattered across multiple continents, with significant deposits found in Australia, South Africa, Canada, and Norway. These mines operate around the clock, employing thousands of workers who dedicate their lives to extracting this precious metal from the Earth's crust. The titanium ore, known as ilmenite and rutile, doesn't look particularly impressive when it first emerges from the ground. It appears as dark, sandy material mixed with other minerals in Earth, giving no indication of the sleek, sophisticated product it will eventually become. Enormous trucks, some weighing hundreds of tons when fully loaded, transport the raw ore from the mining pits to nearby processing facilities where the first stages of refinement begin. At these initial processing plants, the ore undergoes a series of chemical treatments designed to separate the titanium from other elements. The Kroll process, developed in the 1940s, remains the primary method for producing pure titanium metal. During this process, the ore is first converted to titanium tetrachloride through a reaction with chlorine gas and carbon. This intermediate compound is then reduced using magnesium metal in an argon atmosphere, resulting in pure titanium sponge. The entire procedure requires maintaining temperatures exceeding 1000 degrees Celsius and must be conducted in carefully controlled environments to prevent contamination. The resulting titanium sponge looks nothing like the smooth metal frames we see in smartphones. Instead, it resembles a porous grayish mass that requires further processing before it can be used in manufacturing. From the refining facilities, the titanium sponge is transported to specialized foundries where it undergoes vacuum arc remelting. This sophisticated technique involves placing the titanium in a water-cooled copper crucible and melting it using an electric arc while maintaining a vacuum or inert gas atmosphere. The vacuum environment is crucial because titanium readily reacts with oxygen and nitrogen at high temperatures, which would compromise its structural integrity and introduce impurities that could affect the final product's quality. The molten titanium is then cast into large cylindrical ingots, some weighing several thousand kilograms, which are allowed to cool slowly under controlled conditions to ensure uniform crystalline structure throughout the metal. These massive titanium ingots then embark on another journey, traveling by ship, rail, and truck to Apple's designated manufacturing partners, primarily located in China. The logistics involved in transporting such valuable materials are immense, with specialized containers, tracking systems, and security protocols ensuring that every kilogram of titanium is accounted for throughout its journey. Upon arrival at the manufacturing facility, the ingots are stored in climate-controlled warehouses, where they await their turn to enter the production line. Quality control teams immediately begin testing samples from each shipment, checking for purity levels, structural consistency, and any signs of contamination that might have occurred during transport. Using computer-controlled CNC machines, the tough titanium blocks are precisely cut and shaped into the phone's frame. The process is so accurate that even the smallest error is unacceptable. Because cutting titanium generates intense heat, special cooling systems are used throughout the process. After shaping, robotic arms move the frame to polishing units, where it is smoothed and refined into a sleek premium finish. The CNC machining centers that transform raw titanium into iPhone frames represent some of the most advanced manufacturing equipment ever created. Each machine costs millions of dollars and requires highly trained operators who have undergone years of specialized training to understand both the equipment and the unique properties of titanium. The programming alone for cutting a single iPhone frame involves thousands of lines of code, specifying every movement of the cutting tool with micrometer precision. Engineers spend months perfecting these programs, running countless simulations and test cuts before the actual production begins. The cutting tools themselves are made from tungsten carbide or polycrystalline diamond, materials hard enough to withstand the demands of cutting through aerospace-grade titanium. The cooling systems employed during machining are equally sophisticated, using a combination of high-pressure liquid coolant and precisely directed air streams to manage the tremendous heat generated when cutting tools meet titanium. Without proper cooling, the friction would cause the titanium to work harden, making it even more difficult to cut while simultaneously dulling the expensive tooling. The coolant is continuously filtered and recycled through the system, with sensors monitoring its temperature, flow rate, and chemical composition to ensure optimal performance. Any deviation from the specified parameters triggers automatic adjustments, and in severe cases, the machine will halt production entirely until operators can investigate and resolve the issue.
As each frame emerges from the CNC machines, it carries the distinctive marks of the machining process. Tiny ridges and tool marks that, while invisible to the naked eye, would be unacceptable in a premium product. This is where the polishing process becomes essential, transforming the machined frame into the smooth, refined surface that consumers expect from an Apple product. The polishing operation involves multiple stages, beginning with abrasive belts that remove the most prominent machining marks and progressing through increasingly fine polishing compounds until the surface achieves a mirror-like finish. Robotic arms handle the frames throughout this process, applying consistent pressure and movement patterns that human workers could never maintain over thousands of units. Next comes the coloring process, which is far more advanced than regular painting. Instead of applying a simple coat, a special technique is used where color particles bond directly with the metal at a molecular level. This is how the unique orange titanium finish is created: durable, vibrant, and resistant to wear. The physical vapor deposition process used to create the orange titanium finish represents a remarkable achievement in material science. Inside vacuum chambers the size of small rooms, the polished titanium frames are carefully positioned on rotating fixtures that ensure even coverage from all angles. Technicians wearing full cleanroom suits handle each frame with gloved hands, inspecting them under specialized lighting for any defects that might have escaped earlier quality checks. Once loaded into the chamber, the air is pumped out until a near-perfect vacuum is achieved, removing virtually all atmospheric contamination that could interfere with the coating process. Within this vacuum environment, specialized materials are heated until they vaporize, creating clouds of atoms that travel through the chamber and deposit themselves onto the titanium surface. For the orange titanium finish, a precise combination of metallic compounds is vaporized in carefully controlled sequences, with each layer measuring just nanometers in thickness. The orange coloration emerges from the interaction of light with these incredibly thin films, a phenomenon known as thin film interference. By controlling the thickness and composition of each layer with atomic precision, engineers can create colors that would be impossible to achieve through traditional painting or anodizing methods. The resulting finish is not merely sitting on top of the titanium, it has become part of the metal itself, integrated at the molecular level in a bond that will last for years of normal use. The PVD coating process takes several hours for each batch of frames, with sophisticated monitoring systems tracking hundreds of parameters throughout the operation. Temperature sensors, pressure gauges, and spectroscopic analyzers continuously feed data to computerized control systems that make real-time adjustments to maintain optimal coating conditions. Even the slightest variation in chamber pressure or source material temperature could result in color inconsistencies that would render the frames unsuitable for use in premium devices. Quality control is especially rigorous during this phase, with sample frames from each batch undergoing extensive testing for color accuracy, coating adhesion, and wear resistance before the entire batch is approved for further processing. Meanwhile, in another section of the factory, the most important part of the phone is being built: its brain, the motherboard. Inside a controlled cleanroom environment, robots and skilled technicians work together to place thousands of tiny electronic components onto circuit boards. A powerful processor is then installed,
enabling the device to perform at high speed and efficiency.
The clean rooms where iPhone motherboards are assembled operate under conditions more stringent than most hospital operating rooms. The air is filtered through high-efficiency particulate air filters that remove 99.97% of all particles larger than 0.3 micrometers, creating an environment where even microscopic contamination is virtually eliminated. Workers entering these spaces must pass through air showers that blast away any loose particles from their clean room suits, and they must follow strict protocols regarding movement, speaking, and personal hygiene. The temperature is maintained at exactly 21 degrees Celsius, and humidity is controlled to within a few percentage points to prevent static electricity buildup that could damage sensitive components. The motherboard fabrication process begins with the production of the printed circuit boards themselves, complex multi-layered structures that serve as the foundation for all electronic components. These boards are manufactured using a photolithographic process similar to that used in semiconductor fabrication, with copper traces etched onto fiberglass substrates in patterns so fine that they can only be seen under magnification. Each motherboard contains dozens of layers, bonded together under heat and pressure, with microscopic holes called vias connecting traces between layers. The precision required is extraordinary. Traces may be only 50 micrometers wide, with spacing of similar dimensions, and any defect in the manufacturing process could render the entire board useless. Once the bare circuit boards are ready, the component placement process begins. Surface mount technology machines, capable of placing tens of thousands of components per hour, work continuously to populate the boards with resistors, capacitors, inductors, and integrated circuits. These machines use computer vision systems to identify each component from reels containing thousands of parts, picking them up with vacuum nozzles, and placing them onto the board with positional accuracy measured in micrometers. The smallest components are barely visible to the human eye, measuring just 0.4 millimeters in length. Yet each must be placed precisely on its designated pad if the device is to function correctly. The A-series processor that serves as the iPhone's brain represents years of research and development by Apple's chip design teams. Manufactured using advanced semiconductor processes at foundries in Taiwan, these chips contain billions of transistors packed onto a silicon die smaller than a fingernail. The processor arrives at the assembly facility already encased in its protective package, but installing it onto the motherboard requires exceptional precision. Ball grid array technology connects the processor to the board through hundreds of tiny solder balls arranged in precise patterns on the chip's underside. During the reflow soldering process, these balls melt and form permanent connections with corresponding pads on the motherboard, creating electrical pathways that will carry billions of signals per second during normal operation. After component placement, the populated boards pass through reflow ovens that heat them to precisely controlled temperature profiles, melting the solder paste that was applied earlier and creating permanent connections between components and board. The temperature must be raised gradually to prevent thermal shock, maintained at peak for just long enough to ensure proper solder flow, and then cooled at controlled rates to prevent stress damage. Multiple thermocouples monitor temperatures throughout the oven, and the conveyor speed is carefully calibrated to ensure each board receives exactly the right thermal treatment. Following reflow, automated optical inspection systems examine every solder joint, comparing them against reference images to identify any defects that require rework. At the same time, the camera system, one of the most advanced parts of the phone, is assembled separately. Lenses, sensors, and stabilization components are carefully integrated before being mounted onto the device. The battery is also installed along with numerous delicate internal connections, all handled with extreme precision. The camera module assembly process takes place in dedicated facilities, where cleanliness standards are even higher than those in the main electronics assembly areas. Optical components are extraordinarily sensitive to contamination. A single dust particle trapped between lens elements would appear as a visible spot in photographs, rendering the entire module defective. Workers in these areas wear additional protective gear, including face masks and finger cots,
And workstations are equipped with localized air filtration systems that create ultra-clean zones immediately around the work surface. The camera sensors themselves are marvels of semiconductor engineering, containing millions of individual pixels, each capable of capturing light and converting it to electrical signals. These sensors are manufactured in specialized semiconductor fabrication facilities, using processes that have been refined over decades to maximize light sensitivity while minimizing noise. The sensor die is mounted onto a ceramic substrate that provides both electrical connections and mechanical stability, and a precision cover glass is attached to protect the delicate sensor surface while allowing light to pass through unimpeded. Infrared filtering coatings on this glass prevent unwanted wavelengths from reaching the sensor and affecting image quality. The lens assembly process requires equally impressive precision. Multiple lens elements made from specialized optical glass or advanced polymer materials must be aligned to within micrometers of their designed positions. Each element is carefully inspected for optical quality before assembly, with automated systems measuring surface accuracy, coating uniformity, and material clarity. Aspherical lens elements, whose complex curves are calculated using sophisticated optical design software, are particularly challenging to manufacture and inspect. These elements correct for aberrations that would otherwise degrade image quality, enabling the compact camera modules to capture photographs that rival those from much larger traditional cameras.
Optical image stabilization systems add another layer of complexity to the camera module. Tiny actuators, usually based on voice coil motor technology, move the lens elements or sensor in response to detected motion, compensating for handshake and other movements that would otherwise cause blur. These actuators must respond within milliseconds to signals from gyroscope sensors that continuously monitor the phone's orientation and movement. The entire stabilization system, including actuators, position sensors, and control electronics, is integrated into the camera module in a package measuring just a few millimeters in thickness. The battery installation process occurs in yet another specialized area of the factory, where safety considerations take precedence over all other concerns. Lithium-ion batteries, while offering exceptional energy density, can be dangerous if damaged or improperly handled. Assembly workers receive extensive training in battery safety, and the work areas are equipped with fire suppression systems, protective barriers, and emergency protocols. Each battery cell is tested before installation, with automated systems checking voltage, internal resistance, and physical integrity. The batteries are secured within the device using precisely applied adhesive strips that ensure the cell remains firmly in place during normal use, while still allowing for removal during recycling or repair operations.
The internal connections that link various components within the iPhone are made using flexible printed circuits, thin ribbon-like cables that can bend and fold to fit within the device's tight confines. These flex cables are manufactured using processes similar to those for rigid circuit boards, but employ flexible polyamide substrates that can withstand repeated bending without damage. Connectors at the ends of these cables snap into receptacles on the various components, creating secure electrical connections that can withstand vibration and thermal cycling. The routing of these cables within the device is carefully planned to minimize interference between different signals while ensuring reliable performance throughout the product's lifetime. Finally, the display is added, completing the device. Before attaching it, a special sealing layer is applied around the edges to protect against water and dust. The screen is then pressed firmly into place, making the phone durable and secure. The display assembly represents the final major component integration in the iPhone manufacturing process. The screens themselves are produced in massive display fabrication facilities, primarily located in South Korea and China, where OLED panels are manufactured using complex deposition processes. Each display consists of millions of organic light-emitting diodes arranged in precise patterns, with red, green, and blue subpixels combining to create the full color gamut that users experience. The manufacturing process for these panels requires extraordinary precision, as defects in even a small number of pixels can render an entire display unusable for a premium device.